Good morning, students. Yesterday, we are discussed up to the general physical properties of alkali metals. Now, we move to chemical properties of alkali metals. So, alkali metals are highly reactive because of the presence of only one valence electron. They possess low ionization enthalpy. That's why they are highly reactive metals, and that reactivity gradually increases as down the group. We know that as the size of the atom increases, that valence electrons can easily participate in the reaction. That's why the chemical reactivity down the group increases. So first of all, the reactivity towards air. So that atmospheric air contains oxygen and nitrogen. If alkali metals are placed in the dry air, they will be tarnished. That color will be shaded due to the atmospheric air, due to the formation of oxides. When alkali metals reacts with moisture, they form hydroxides. So here, especially the top of the element lithium forms only monoxide, that is lithium monoxide, having a formula of Li2O. Whereas the second element sodium, that forms monoxide with limited supply of oxygen, whereas in case of excess of oxygen it forms dioxide. Okay, so let us observe the equation. That lithium forms lithium monoxide, whereas that sodium forms with limited supply of oxygen, it forms sodium monoxide. In case of excess of oxygen, it forms peroxide, sodium peroxide. The rest of the others, that means potassium, rubidium, cesium, they mainly form superoxides. So in all these oxides, the oxidation state of the alkali metal is +1. So here that lithium shows exceptional behavior reacting directly with nitrogen, which is present in the atmospheric air. Already we are discussing that oxygen reactivity along with nitrogen is also present in atmospheric air. It forms nitride having a formula of Li3N, lithium nitride. Here, the three types of oxides, especially in case of normal oxides, that oxygen carries -2. In case of peroxides, it forms O2 -2. In case of superoxides, it forms O2-. So here, that normal oxide ion is in the form of O-2. Peroxide ion is in the form of O2-2. Superoxide, that superoxide has a formula of O2-. This superoxide, in this superoxide, that oxidation state of oxygen will be -1/2. In case of peroxide, that oxidation state of oxygen is -1. In a normal oxides, its oxidation number is -2. So here different oxidation states exhibited by the oxygen. So normally that frequently asked question, what is the oxidation state of potassium in superoxide? Here we said already all alkali metals, they exhibit +1 oxidation state. Here they are asking only about the oxidation state of potassium. So here that potassium or rubidium or cesium, any alkali metal that can form +1 oxidation state. If they ask the oxidation state of oxygen, so here that oxygen is in the form of O2-. That O2- indicates it is a superoxide. That superoxide ion exhibit -1/2 is the oxidation state. So in superoxides, oxygen exhibits a -1 oxidation state. After that, Second reaction, reactivity towards water. So alkali metals react with water, they form hydroxides. So generally that hydroxides possess basic nature. So alkali metal hydroxides forms that basic hydroxides along with the liberation of hydrogen gas. Along with the liberation of hydrogen gas. Generally the reactivity of the elements, especially those elements are nothing but alkali metals from lithium to cesium, because francium is a radioactive element. So that reactivity towards water gradually decreases from top to bottom. So here lithium has the most negative E standard value, already we are discussed in previous class. So that's why that reactivity to water is very less, whereas sodium has the least negative value among the alkali metals. That's why lithium has small size and very hydration energy, whereas the other metals will be reacts explosively. For example, in case of lithium, it forms hydroxide of the formula LiOH. The formation of lithium hydroxide will be little bit slower, whereas that sodium reacts with water vigorously and forms NaOH. That reactivity of sodium is more vigorous with water and produce sodium hydroxide. Along these hydroxides, commonly used gas is hydrogen gas. At the bottom of the element, that cesium forms cesium hydroxide along with the liberation of hydrogen gas. So in all these, the reactivity gradually increases from lithium to cesium, because that smaller lithium will form or hydrated with water more easily. That's why the reactivity of these alkali metals will gradually increases. So in free state, the order of reactivity, in free state, the order of reactivity of these alkali metals are from lithium to sodium increases, sodium to potassium, potassium to rubidium, and rubidium to cesium. So cesium is the more reactive and lithium is the less reactive in free state. Okay. And these alkali metals can also react with proton donors like alcohols. Actually alcohol projects ROH group. So here free proton group will be available. Along that gaseous ammonia, here also proton is available. And alkynes, that alkynes possess acidic hydrogens. Let us take, this is the alkynes general formula. In this one acidic hydrogen is present. So like that all are proton donors. So alkali metals react with these proton donors also. Okay. After that, coming to the third one, that reactivity towards hydrogen. So with the hydrogen they form hydrides. Generally these hydrides will be ionic nature. So here that all alkali metals hydrides are ionic solids with high melting. So here that reaction of hydrogen with lithium will be takes place at higher temperature, almost 1073 Kelvin, whereas the rest of the others will be reactive with around 673 Kelvin. So this indicates the less reactivity of lithium with dihydrogen. So all these form ionic solids having a formula M plus and H minus. We know that in metal hydrides hydrogen always carries negative charge. Here that oxidation state of hydrogen is -1, whereas that alkali metal has +1. So in all metal hydrides hydrogen exhibits -1 oxidation state, whereas in case of other elements the hydrogen exhibits +1 oxidation states in its compounds. Okay. Now we go to the another reaction, that is reactivity towards halogens. So actually halogens are 17th group elements. They contain 7 valence electrons. So only one electron is short to reach the nearest inert gas configuration. That's why they are also highly reactive. So they react with alkali metals very easily. So they form alkyl halides of this metal halides of this formula MX type. They form metal halides of this general formula MX. Actually all these are ionic, but in case of lithium, due to of its small size, somewhat it has covalent character. So alkali metals can form the halides of the formula M plus and X minus. Here in case of lithium, that lithium halides will be covalent nature due to the small size of lithium ion, due to the small size of lithium ion. So already we know the ionic character or covalent character can be identified by using Fazan's rules. So according to Fazan's rules, smaller the size of the cation and larger the size of the anion, covalent character is more. That's why the compound formed by the lithium will be covalent nature, especially in case of lithium iodide. We know the formula of the lithium iodide, Li. So in that lithium iodide, that iodide ion is the larger anion and the lithium ion is the smaller cation. So that bond exists between the cation and the anion. Cation with small size and anion with larger size will form covalent character. That's why among the halides of lithium down the group, that covalent character increases. And one more thing here, you must be know that lithium is the small size. That's why it has more tendency to attract the anionic cloud towards itself. That's why that larger anion can be easily distorted by the smaller cation and forms more covalent character. So except lithium, remaining all metal halides will possess ionic character. Only lithium halides will be possess covalent character. Coming to the reducing nature, actually we can discuss that reducing nature based on the SRP value, standard reduction potential values. So here that highest standard reduction potential value possessed by the lithium, so more negative SRP value exhibited by the lithium. That's why in aqueous solution, the order of reducing power can be written as, in aqueous solution, the order of reducing power can be written as lithium is the strong reducing agent, after that rubidium, after that cesium, after that potassium, and the lowest reducing nature exhibited by the sodium. So in previous class we are discussed that values of SRP values of alkali metals. Among that, lithium has more negative SRP value. Lithium has more negative SRP value, whereas sodium has the least SRP value. Sodium has a least negative SRP value. That's why the reducing power in aqueous solution can be measured basing on the SRP value. Actually, that reducing power can be involved in the different steps. So in first step, that a solid alkali metal can be converted into the gaseous metal, which is nothing but sublimation enthalpy. From that gaseous atom, we can remove the electron, that indicates the ionization enthalpy. Now by adding of the water to produce the aqueous state, from the gaseous state to aqueous state, that is nothing but the hydration enthalpy. First two are the positive values, that means their enthalpy will be positive, indicates endothermic process, and the last step indicates the hydration enthalpy, that the delta H value is negative. So which is more for lithium. That's why due to of its small size, lithium is more hydrated, that the hydration enthalpy of lithium is very high. That's why resultant that SRP value of alkali metals will be exhibited by highest by the lithium and the lowest one exhibited by the sodium. Okay. After the reducing nature, we go to one more important point, that is that reaction with liquid ammonia. So it is one of the more important reason. So questions will be frequently asked from this topic. So here basically alkali metals when placed in liquid ammonia, they give a deep blue color solution and exhibit conducting nature. Generally that conducting nature is due to the ammoniated electrons, and color is also due to that ammoniated electron. So here the blue color of the solution is due to ammoniated electron. So let us observe the above equation. M indicates alkali metal that can be react with liquid ammonia. It produces a complex. Let us take M NH3 taken X times. Here that M carries positive charge. That's why ammonia is neutral and that carries positive charge. Along that, electrons are released from the metal valency. That electron is also solvated by the ammonia. That's why we call it as ammoniated electrons. So these ammoniated electrons are responsible for the color of the solution. Here the color of the solution is blue color. Along that, the presence of ammoniated electron that exhibit conductivity also. Okay. So here, because of the presence of unpaired electrons, the solution exhibit paramagnetic nature. And long standing, this solution will liberate hydrogen gas and forms amide. So on long standing, this solution liberates hydrogen gas due to the formation of amide. So here that ammoniated metal ion will gains the electron in presence of the solvent ammonia. It gives amide, metal amide, along with the liberation of hydrogen gas. And one more thing, the blue color of the solution will be changes to bronze on heating. So whenever that concentrated solution or on heating, the blue color of the solution changes to bronze color and becomes to diamagnetic. That means the solution can lose its paramagnetic nature. So these are the general properties of the alkali metals with hydrogen, halogens and liquid ammonia. Coming to the uses of the alkali metals. So mostly lithium can be used in making white metal. Actually that white metal is obtained by reacting with lithium with lead, which can be used in motor engines manufacturing, bearings. Okay. And aluminum make aircrafts, and with magnesium it make armor plates. Armor plates are nothing but bulletproof plates. So that bulletproof materials can be obtained by making reaction with lithium with magnesium, and also can be used in thermonuclear reactions. That sodium can be used as tetraethyl lead. Actually these are the tetramethyl lead are the anti-knocking agents in vehicles. So nowadays that anti-knocking agents are not required because of we are using the unleaded petrol. So in previous days, olden days, that leaded petrol can be used. At that situation, that tetraethyl lead B can be used, or tetramethyl lead can be used as an anti-knocking agent. So nowadays we can use the lead-free petrol. That's why no need to use the tetraethyl lead. And a liquid sodium metal used as a coolant in fast breeder nuclear reactors. So in nuclear reactions takes place, that fast moving neutrons will be released. So those can be controlled by using the liquid sodium metal. So this is about the uses of sodium. Coming to the uses of potassium, potassium has so many number of uses, especially in biological system they can be take part, and also that potassium chloride can be used as a fertilizer for agriculture sector, and potassium hydroxide is used in the manufacture of soft soaps, especially that baby soaps are made with potassium hydroxide. So because of soft nature, it is harmless to kids. And that potassium can be used as an excellent adsorbent of carbon dioxide, and cesium can be used as a photoelectric cells. So that normally photoelectric cells, they can produce photoelectrons. So here cesium can easily loses the one valence electron. So each cesium atom can contribute one electron easily. That's why it can be used in photoelectric cells. So these are the common uses of the alkali metals. After that, we go to the compounds. So generally that compounds of the alkali metals will be of different types. So first of all, we go to the oxides and hydroxides. Already we learned how can that oxides and hydroxide are produced. So whenever that alkali metals are placed in atmospheric air, they can form monoxides, peroxides and superoxides having different formula. So these oxides ability gradually decreases, especially that superoxide ability can be formed by the bottom of the elements that potassium, rubidium, cesium. The main reason is the larger anion, that means peroxide ion is normal oxide is O2 minus O minus 2, normal oxide, peroxide is O2 minus 2 and superoxide is O2 minus. So here that superoxide ion can be stabilized by the larger cations. So a larger anion can easily stabilize the larger cation. That's why as down the group, the formation ability of superoxides will be increases. Okay. So When these oxides can be undergo hydrolysis, they produce hydroxides. For example, monoxide can hydrolysis produce alkali metal hydroxide. Not only that monoxide, peroxides and superoxide also dissolve in water. They produce hydroxides. Along that, liberation of oxygen in case of superoxide. So these are the common reactions of formation of hydroxides. So actually these oxides and peroxides are colorless, but superoxides are yellow or orange color. This point also very important. So here the superoxides also exhibit paramagnetic nature. This is mainly due to the presence of one unpaired electron in antibonding molecular orbital of p orbital. So here an example is discussed. In that example, that KOT is paramagnetic. Why? So that superoxide ion is paramagnetic because of the one unpaired electron present in antibonding molecular orbital of pi star of 2p orbital. So already this concept can be discussed in chemical bonding molecular orbital theory. So in this way, that oxides when dissolved in water, they produce hydroxides. So not only monoxide, peroxides and superoxides can also form this type of reaction. After that, coming to the halides. So that formation of halides can be directly taking the reaction between the metal with the halogen. So here that metal halides having the formula Mx, where X is nothing but the halogen, fluorine, chlorine, bromine and iodine. So coming to the nature of these halides, all have high melting point, colorless, and they have crystalline solids. So they can be also prepared by the reaction of the appropriate oxide, hydroxide, carbonate with aqueous hydrohalic solution. Hydrohalic solution having a general formula HX. And one more thing, here that formation values of these group elements will be negative. Coming to the fluorides, let us take lithium fluoride, sodium fluoride, magnesium fluoride, lithium, sodium, potassium fluoride. Potassium fluoride, rubidium fluoride, cesium fluoride. From top to bottom, the formation values are negative. These fluorides becomes less negative as down the group. That means from top to bottom, we move from that delta formation of H standard is more negative to less negative. Whereas in case of other halogens, let us take either chlorine, bromine and iodine, the reverse is true. For example, LiX, NaX, KX, RbX, cesium X, where X is nothing but chloride ion, bromide ion or iodide ion. Here the reverse of the above is true. That means that delta formation values of these group, these are also negative, but here you are moved from less negative to more negative, less negative to more negative. In previous case, more negative to less negative, whereas in case of chlorides and bromides and iodides, the reverse of the fluorides will be true. That means from top to bottom, that formation values of these halides will move from less negative to more negative. If we compare with the same metal with different halogens, then fluoride has a more negative value when compared with the rest of the others. That's why from fluoride to iodide, for a corresponding metal, that formation values becomes less negative from fluoride to iodide. So this is the general thing. And coming to the nature, so actually these halides possess high boiling point and melting point. The order of boiling points are in the range of fluorides more than chlorides, chlorides more than bromides, bromides more than iodides. That means highest melting and boiling points possessed by the fluorides and least can be exhibited by the iodides. Actually, all these are soluble in water. All these alkyl halides are soluble in water. So, in that there is an important point, why the solubility of lithium fluoride is less in water, and also that less solubility of cesium iodide in water. These 2 points are very, very important. So, frequently these 2 questions will be appeared in the as a statement. So, here that solubility of lithium fluoride is very low because of high lattice enthalpy. So, the solubility of lithium fluoride is low. Low solubility is due to high lattice enthalpy. So, due to that lattice enthalpy, the bond between lithium and fluorine is very strong. That's why that breaking will be required more amount of energy. That's why the solubility is low. Whereas in case of cesium iodide, that iodide is the larger ion. That larger ion has the low hydration enthalpy. So, due to the low hydration enthalpy of iodide ion, that's why the solubility of cesium is low, because that anion is larger size as well as cation is also larger size. So, both the ions have low hydration enthalpy. That's why the solubility of cesium iodide in water is low, whereas lithium fluoride is also less soluble in water due to of its high lattice enthalpy. 2 important points will be asked frequently from this topic. And the other halides of lithium are also soluble in ethanol. Ethanol is a alcoholic group, acetone and ethyl acetate, and especially that lithium chloride is soluble in pyridine also. Actually, pyridine is an organic compound. So, already we are discussed about the nature of the halides of lithium, especially lithium halides are covalent nature. That's why they are less soluble in water, more soluble in organic solvents, because lithium chloride has a non-polar nature. That's why it is soluble in non-polar solvent like pyridine. So, this is all about the halides. Coming to the reaction with the oxo acids. So, generally oxo acids are nothing but proton donating substances. Let us take carbonic acid H2CO3. So, here 2 protons will be available, whereas in case of sulfuric acid it is also 2 protons are available. So, to this the alkali metals can act as a acids or bases, because metals have basic nature. That's why they can easily react with acids, especially in case of oxo acids. It forms 2 types of salts. Generally, we know that the reaction between an acid and base produces salt and water. Here also that metals possess the basic nature. Due to their basic nature, they can be easily attacked by the acids, especially like oxo acids. So, here that oxo acids can form the salts with alkali metals. So, here 2 types of salts are mentioned. One is carbonates having a formula M2CO3, and another one is hydrogen carbonate MHCO3. So, here these 2 types of compounds will be formed when alkali metals react with a carbonic acid. Similarly, it can be also form salts with the sulfuric acid also. So, in this way that hydrogen carbonates stability gradually increases from top to bottom. So, here that electropositive character, that means as the size of the atom increases, electropositive character increases, as down the group electropositive group character increases in this group. That's why the stability of the carbonates and hydrogen carbonates also increases. One more important point here. So, when you compare the stability of carbonates or bicarbonates, bicarbonates are nothing but hydrogen carbonates. So, those carbonates and hydrogen bicarbonate stability gradually increases from top to bottom. Actually, that hydrogen carbonates will be in solid state except lithium. So here that lithium carbonate or lithium hydrogen carbonate both will be in the liquid state. Okay. So here that these hydrogen carbonates and bicarbonates or carbonates will be undergo decomposition to produce oxides and carbon dioxide gas will be released. Coming to the anomalous behavior. In every group, the top of the element exhibits somewhat different properties than the rest of the other elements in that group. Originally, the group elements will possess the same chemical properties because of the similar outermost electronic configuration. But when compared with the rest of the other elements, in each group, the top of the element will exhibit somewhat different properties than the rest of the other elements in the same group. This is nothing but anomalous behavior. Okay. So, what are the reasons for anomalous behavior? Because of the small size of the atom and high electronegativity of the atom, top of the element. And number 3, absence of d orbitals, and 4, high polarizing power. So, basing on these 4 properties, the top of the element will always exhibit somewhat different properties than the rest of the other elements in that group. So, here the top of the element in this group is lithium. That lithium exhibits somewhat different properties than the rest of the other elements in this group. Here some points will be discussed because of the anomalous behavior. So, first thing is lithium is the much harder and have melting and boiling point is high when compared with other alkali metals. Actually, alkali metals are very soft, even they cut with a knife also. As down the group, that softness increases on top of the element lithium is much harder. That's why it has a high melting and boiling point. And second thing is lithium is the highest reactive element in this group and is a strong reducing agent among all the alkali metals. And it can be directly combined with nitrogen, atmospheric air and air, oxygen to form oxides and nitrides, whereas the other elements that cannot form such type of ability. So the only element in this group, lithium, can directly combine with air to form lithium monoxide and lithium nitride. And third one is the lithium chloride is deliquescent. That means actually water molecules will be trapped in that. That's why it can be crystallized as LiCl2H2O. So whenever we can place so here ఒకసారి నోట్. So here we are discussing about the anomalous behavior of lithium. So in that lithium chloride has a deliquescent nature. So here that deliquescent nature indicates that hydrated water molecules will be melt. So that nature is said to be deliquescent. Whereas the remaining alkali metals do not form such type of hydrides. The only lithium can form such type of hydrates. So that hydrates cannot be formed by the other alkali metals, only lithium can form. And hydrogen carbonate is not obtained in solid state, it can be a liquid state, while the other elements can form solid hydrogen carbonates. And one more thing, lithium, unlike other alkali metals, forms no ethanides on reaction with ethane. So this point is already discussed in junior organic chemistry. So let us take ethane. Ethane having a formula of CH triple bond CH. It has one acidic hydrogen at each carbon. Those acidic hydrogens can be replaced by the sodium or potassium or rubidium or so on, but not lithium. So when sodium can form ethanide by replacing the hydrogen, so actually it is called acetylide. It is a diacetylide compound. That acidic hydrogens can be replaced by the alkali metals, especially from sodium onwards, but lithium cannot displace the acidic hydrogen. And the sixth one, that lithium nitrate on heating gives lithium oxide, whereas the other alkyl nitrates will be decomposed to give corresponding nitrites. So there is a difference between the nitrates of lithium and sodium. That lithium nitrate will liberate oxygen, and other nitrates also liberate oxygen. The only difference is lithium nitrate will produce lithium monoxide along with liberation of nitrogen dioxide gas, whereas other nitrates will changes to nitrites. So here that sodium nitrate will be changes to sodium nitrite along with the liberation of oxygen. That is the difference. And the last one, lithium fluoride and lithium monoxide are comparatively much less soluble in water than the corresponding compounds of the other element. That means that solubility of lithium fluoride is always less. Already this point is discussed in the previous topic. And lithium monoxide are also less soluble in water when compared with other alkalis. So especially these points must be very important. So you must remember these 2 points. After that, going to the similarity of lithium and magnesium. Actually, lithium is diagonally related with magnesium. So in periodic classification, we know the diagonal relationship. That means lithium, sodium, potassium. These are the 1A group. Beryllium, magnesium, calcium, 2A group. Boron, aluminum, gallium, 3rd A group. Carbon, silicon, germanium, 4th A group. So here that lithium is diagonally related to magnesium, and beryllium is diagonally related to aluminum, boron is diagonally related to silicon. Here the sizes of these ions, let us take for lithium it is a Li plus, magnesium plus 2, beryllium plus 2 and Al plus 3, boron plus 3 and silicon plus 4. So here that sizes of these species, will be almost nearly same. That's why even though they do not belong to the same group, they exhibit a similar type of reactions. That is nothing but a diagonal relationship. So here that the points of similarity between the lithium and magnesium will be considered. So both lithium and magnesium will be harder. Whereas and lighter than the other elements in the respective group. Coming to the second point, lithium and magnesium react slowly with water. That reactivity of lithium and magnesium will be slow with water, and their oxides and hydroxides are much less soluble in, and their hydroxide decomposes on heating. So here one more similarity is both lithium and magnesium can form nitrites when direct combination with nitrogen. So lithium nitrate having a formula of Li3n, magnesium have a formula of Mg3n2. So these can be obtained by the direct combination. Coming to the oxides, these two oxides do not combine with the excess of oxygen to give any superoxide. That means lithium will be always forms monoxide and magnesium also MgO. They do not form any superoxides. Coming to the third point, the carbonates of lithium and magnesium decomposes mainly to produce the oxides and carbon dioxide, and these two do not form the solid hydrogen carbonates, both lithium and magnesium do not form the hydrogen carbonates in the solid state. Mostly they are in the liquid state. And both lithium chloride and magnesium chloride are soluble in ethanol alcohol soluble, and both are deliquescent because they form the hydrates. Already we are discussed in the that anomalous behavior of lithium. So lithium can form LiCl2H2O, whereas magnesium form MgCl2 with 8H2O. So these are the general common things that will be observed between the lithium and magnesium. So these two mainly related to due to the diagonal relationship. After that we go to the compounds. In that compounds, washing soda having a formula of Na2CO3, it is a decahydrated molecule. So mostly that sodium carbonate can be prepared by using the Solvay's process. So the main thing principle involved here, the slow solubility of sodium hydrogen carbonate. So here the solubility of sodium hydrogen carbonate in solution will be low. That's why it is easy to separate and extract the sodium hydroxide decahydrated. Whereas that similar compound KHCO3, that is nothing but potassium hydrogen carbonate, is not possible because of its high solubility. So there is a similar question definitely asked, that is which can be used Solvay's method, Solvay's soda Solvay process method for the extraction of carbonates, that is only possible to sodium carbonate but not potassium carbonate. The main reason is during the extraction of sodium carbonate, that compound of sodium hydrogen carbonate will have low solubility. That's why it can be separated from the solution. Whereas in case of potassium hydrogen carbonate, the solubility will be high and the solution will not separated from that compound. So that is the main reason. So here that general reactions in this sodium carbonate extract will be identified as the raw materials can be used as ammonia, carbon dioxide is the main raw material. Along that brine solution can be used, sodium chloride is the brine solution. Here that various reactions will be takes place. In first step, that ammonia will combine it with that carbon dioxide and water vapor, it produces ammonium carbonate. That formed ammonium carbonate will be saturated with carbon dioxide, it produces ammonium bicarbonate NH4HCO3. So now this ammonium bicarbonate is treated with brine solution or sodium chloride solution, it produces NH4Cl solution, along that NaHCO3. This NaHCO3 is separated or precipitated due to the low solubility. That's why we can separate the sodium bicarbonate, and heating that sodium bicarbonate will produce the sodium carbonate. This is the main equation, that heating of the sodium bicarbonate will produce sodium carbonate along with the liberation of carbon dioxide and water vapor. And here that ammonia can be recovered or regenerated by treating the solution ammonium chloride with calcium hydroxide. That calcium hydroxide will treated with ammonium chloride, it liberates ammonia gas along with formation of calcium chloride, CaCl2. So actually the Solvay process is applicable to sodium hydrogen carbonate. Already we are discussed that point, that manufacturing of potassium carbonate cannot be possible by using potassium hydrogen carbonate because two solubility that can be precipitated by the addition of ammonium hydrogen carbonate. That's why this method is not suitable for the preparation of K2CO3. Coming to the properties of sodium carbonate, actually that sodium carbonate is a decahydrated molecule and exists as a white crystalline solid. So this decahydrated sodium carbonate is also known as washing soda. It is readily soluble in water. On heating, gradually it loses the water molecule step by step. On heating, it produces initially that monohydrate. When the temperature is more than 373 Kelvin, that remaining one water molecule will also eliminated to produce soda ash. Soda ash is nothing but that anhydrous Na2CO3. So here up to 375 Kelvin, gradually water molecules will lose and produce sodium carbonate monohydrate. When the temperature is greater than 373 Kelvin, that means more than 375, the remaining water molecule will be also eliminated and produce anhydrous sodium carbonate, we call it as soda ash. So soda ash is nothing but Na2CO3. So here that carbonate ions will be involved in the hydrolysis and produce bicarbonate ion, and normal uses of sodium carbonate is mentioned here. So those will be very easy points. Coming to the second one, sodium chloride, another compound of that alkali metals. Actually that seawater contains huge amount of salts. In that that contribution of sodium chloride will be 2.7 to 2.9%. That mass of the salt will be in the seawater. So approximately huge amount of salts will be collected annually by solar evaporation. So that NaCl raw sodium chloride can be obtained by solar evaporation of seawater. And here one more important point is there. How can you remove the impurities that are present in the sodium chloride crystals? So here we can use the common ion effect. Actually that sodium chloride contains impurities like calcium chloride, magnesium chloride, calcium sulfate, sodium sulfate, like that. All these are impurities. So here that calcium chloride and magnesium chloride impurities, because they are the deliquescent, that means they can absorb water from the atmosphere. So in order to obtain the pure sodium chloride, we can allow the crude salt to dissolve in the minimum amount of water. That means whenever that sodium chloride will be dissolved in water, that produce aqueous ions, that Na plus aqueous and Cl minus aqueous. Okay. Now that can be saturated with a hydrogen chloride gas. So by passing hydrogen chloride gas to this, it produces H plus aqueous and Cl minus aqueous. So by passing of the hydrogen chloride gas, that can be split into chloride ions and H plus ions. Here there is a common ion chloride ion in these two. That's why that common ion effect will be produce pure sodium chloride. That means due to the passage of hydrogen chloride, the chloride ions concentration increases. That's why backward reaction takes place and that pure sodium chloride will be crystallized. So here that sodium chloride can be purified by using common ion effect. So this one is the another important point in this chapter. Coming to the next one, that uses. So generally that sodium chloride can be used as a common salt or table salt for domestic purpose, and it can be used in the preparation of peroxides and sodium hydroxide and sodium carbonate. Coming to the another one, sodium hydroxide, we call it as caustic soda. So whenever it can be falls on the skin, it casticizes the muscles. That's why it is called caustic soda. So here that caustic soda can be prepared by using Kastner-Kellner cell method. So in this Kastner-Kellner method, that mercury can be used as cathode and carbon as anode. So here cathode is mercury and anode is carbon rod, and that mercury can be participate in the reaction. Here that sodium metal will be discharged at a cathode during the combination with mercury in the form of sodium amalgam. So here the cathodic reaction is nothing but we can use the sodium chloride as an electrolyte in this method. That liberated sodium ions will be reached the cathode and gains electron in presence of mercury. It forms sodium amalgam. That is the cathodic product. And at anode, that chloride ions will be reached there. They produce chlorine gas along with the liberation of electrons. Now that sodium amalgam on treating with water, it produces sodium hydroxide along with the liberation of hydrogen gas, and mercury will be collected. So in this way that sodium hydroxide will be prepared. So here that sodium hydroxide will be in white color and is a translucent solid, and melting point is around 591 Kelvin, and is readily soluble in water to give strong alkaline solution. So alkali metals or alkali metal oxides or alkali hydroxides, they dissolve in water, they produce alkaline solution. So here that crystals of sodium hydroxides are deliquescent. So gradually it becomes to liquid whenever it can be that place the pellets of sodium hydroxide on the open vessel. So that sodium hydroxide solution reacts with the carbon dioxide which is present on the surface of the atmosphere to form sodium carbonate. So these are the general things about sodium hydroxide. And also the industrial uses, we can, sodium hydroxide can be used in chemical mainly, and petroleum refining also, in the purification of metals, especially like extraction of aluminum from bauxite, and textile industry, that mercurizing of cotton fabrics, and preparation of pure fats and oils. In this way we can use as a laboratory reagents. So these are the simple uses of the sodium hydroxide. And coming to the another one, another compound of sodium, that is sodium hydrogen carbonate. That sodium hydrogen carbonate is nothing but, sodium hydrogen carbonate is nothing but baking soda. Baking soda. So especially this baking soda is used in manufacturing of cakes. So sodium hydrogen carbonate is also known as baking soda. It decomposes on heating to generate the bubbles of carbon dioxide. So whenever that heating of sodium bicarbonate, it produces Na2CO3 along that H2O and carbon dioxide. So here that carbon dioxide can be evolved as a bubbles. So here that leaving holes of the cakes or pastries and making them light and fluffy. So mainly cakes can be made by using hydrogen carbonate. So he can prepare the sodium hydrogen carbonate by using soda soluble process, or by treating the sodium carbonate with saturated carbon dioxide solution, it produces sodium hydrogen carbonate. So actually that sodium hydrogen carbonate is a mild antiseptic for skin infections and used as fire extinguishers. So mainly that sodium hydrogen carbonate can be used as a fire extinguishers, so which can prevents the fire. So that's why that sodium hydrogen carbonate can be used as fire extinguishers. And finally in this chapter we go to the biological importance of sodium and potassium. Actually these sodium and potassium are very helpful in the pumping of the blood. That pumping of the blood and maintenance of the levels of the ions is very important. So here that sodium potassium pump is very much useful to the a healthy person. So here that potassium ions are the most abundant cations within the cell fluid. They have activate many enzymes and participate in the oxidation of glucose to produce ATP. So here that carbohydrates which is present in the form of glucose can be converted into ATP, adenosine triphosphates, which are the energy units. So with the sodium, they are responsible for the transition of nervous signals. So mainly that nerve signals will be going through the sodium ions. So there is a considerable variation of the concentration of potassium and sodium in the blood levels or in the cell membranes. So here that sodium potassium pumping level will be takes place in a regular manner. So this is the general thing about the sodium potassium pump that across the cell membranes. It is very important point. So this is the general importance of sodium and potassium. So this importance will be very useful in the sodium pumping. So this indicates the completion of the 1A group chapter. Coming to the second A group elements. So in this second A group elements, what is the general outermost configuration? So here NS2 is the general outermost configuration. The elements present in this group are beryllium, magnesium, calcium, strontium, barium and radium. That radium is the radioactive. Each element has a outermost configuration of NS2. So that's why those group elements will possess 2 valency electrons. So here the general physical properties are similar to that of the 1A group elements. So atomic number of different elements in this group are beryllium 4, magnesium 12, calcium 20, strontium 38, barium 56 and radium is 88. So down the group that metallic radius or ionic radius gradually increases and ionization enthalpy gradually decreases. So here IE1 is less than IE2. So that removal of second electron is very difficult when compared with the first electron because of the increase in effective nuclear charge. That is the common point we have known. And coming to the melting and boiling point, there are irregularities in the melting and boiling points. So that boiling point or melting point will be highest for beryllium, whereas the second element magnesium possesses lowest melting point having a value of 924. So that is mainly due to the interactions. So whenever the interactions will be less, that attractive force will be low. And coming to the density will be highest for the last element radium. Gradually that density increases with abnormalities. So here hydration enthalpy of the alkaline earth metals is similar to that of the alkali metals. When compared with the alkali metals, that like alkali metals, the hydration enthalpy of alkali metal ions decreases with increase in the size. So in the similar manner, down the group size of the cation increases. That's why hydration enthalpy gradually decreases. So here that top to bottom hydration levels decreases. Here that magnesium and chlorine exist as a hexahydrated water molecule, whereas that sodium chloride and potassium chloride does not such type of hydrates. So especially the top of the elements magnesium and chlorine will exhibit hexahydrated molecules. And coming to the general physical properties, as down the group that metallic character increases, that alkaline metals are also silvery white, lustrous, that means they will be shine in glow and relatively soft and harder than the alkali metals. So when compared with alkali metals, that alkaline earth metals are very harder. So alkali metals will be the softer one. So beryllium and magnesium will appear as somewhat greyish color. That melting and boiling point of these group are higher than the corresponding alkali metals. So due to of its smaller size. So generally from left to right, atomic size decreases in a particular period. In this manner, that alkali metals possess the larger size when compared with alkaline earth metals, or alkaline earth metals are smaller size when compared with alkali metals. So that's why the ionization enthalpies of these group elements will be higher when compared with the alkali metals, and the metallic nature also will be less when compared with the alkali metals. So here these group elements can also exhibit the color impact. So in this group, that starting beryllium and magnesium cannot exhibit the color due to the strong attractive force of valency electrons with the nucleus. Because of the small size, the valence electrons are strongly held by the nucleus. The color of the compounds will not be there. Whereas the remaining calcium, strontium, barium, they exhibit color. That calcium exhibit brick red color, that crimson red exhibited by the strontium, and apple green color exhibited by the barium. So here these three elements will exhibit the color. Okay. And one more thing, the conductivity of these alkaline earth metals will be compared with the alkali metals. Alkali metals have high electrical and thermal conductivity when compared with alkaline earth metals. Coming to the chemical properties of these group elements, similar to that of first A group elements, they can be also react with atmospheric air and water. So with atmospheric air, beryllium can form barium oxide, which is amphoteric nature. Along that nitrogen form beryllium nitride. So that magnesium is more electropositive and more dazzling with the brilliance of air to give magnesium oxide and magnesium nitride. So only these two elements, beryllium and magnesium, can react with atmospheric air to produce oxides and nitrides. So that oxide formed by the beryllium is amphoteric nature, whereas that magnesium can form magnesium oxide and magnesium nitride. And strontium, barium are readily attacked by the air to form oxide and nitride. They also react with water, increasing the cold to form hydroxides. So here that almost of all elements will react with atmospheric air and water. They form hydroxides with water. Coming to the reactivity towards the halogens, here secondary group elements forms halogens of the type MX2. So in those MX2 type of compounds are directly formed by combination of metal with halogens. So here Another way is also there to produce the fluorides and chlorides. Here that beryllium oxide, which has the amphoteric nature, that will be reactive with the chlorine in presence of carbon, it produces beryllium chloride. So actually that beryllium chloride is covalent character because of its small size. And another reactivity towards with the hydrogen, these group elements forms hydrogens of the type MH2. In that MH2 type compounds, that element group element exhibit +2 oxidation state. So these hydrates can also formed by the reaction of beryllium chloride with lithium aluminum hydride. We know that lithium aluminum hydride is a good reducing agent, especially it can be act as a good reducing agent in organic reactions. So here that beryllium chloride will react with or reduce with lithium aluminum hydride to produce beryllium hydride. So in this way we can prepare the hydrides. After that we go to the reactivity towards acids. So actually these metals has basic character, that's why they can react with easily with acid, and with acids they can liberate hydrogen gas. Okay. Here also the reducing power will be similar to that of alkali metals. When compared with alkali metals, that reducing power of alkali earth metals will be low. So here they also exhibit negative SRP values. That standard reduction potential values of these group elements all will exhibit a negative sign. After that, similar type of reaction will be also identified with the liquid ammonia. So in previous case, that alkali metals they can form blue colored solution with liquid ammonia. On long time it becomes to bronze color. Here also that alkali earth metals will react with liquid ammonia. They produce deep blue black color solutions due to the formation of ammoniated electrons. So here that complex will be also formed. Along that liberated ammonium electrons will exhibit the color. So this is the similar way between the two group elements. One is alkali and alkali earth metals. And general uses can be mentioned here, that is from beryllium onwards to up to calcium barium metals. So you may be observed that the main thing is that magnesium forms alloys with aluminum along with zinc and manganese. Actually that magnesium aluminum alloys has so many uses in the manufacturing of aircrafts. And one more thing is calcium. That calcium can be in the form of compounds. It may be used in metallurgical process for the extraction of metals. So in this way you can use the metal can be reducing agent. Here also that calcium and barium metals owing their reactivity with oxygen and nitrogen at elevated temperature. That means both calcium and barium metals can form oxides and nitrides. And also radium salts can be used in radiotherapy. For example, in the cancer treatment we can use the radium. Okay. After that we go to the general properties of these group elements. Similar to that of alkali metals, they can form oxides and hydroxides. So mainly they can form the oxides of the formula beryllium oxide. Let us take BeO. So beryllium oxide has a amphoteric nature, whereas the remaining all are basic nature. Let us take other elements like magnesium, calcium, strontium, barium. All these form the hydroxides of the type of basic nature, especially beryllium oxide and its compounds are amphoteric nature. So here that solubility of thermal stability of these basic character of hydroxides will be increases with increasing atomic number. That means we are moving from the magnesium hydroxides to barium hydroxide. Definitely that solubility, thermal stability and the basic character of these hydroxides will be gradually increases. So when compared with top of the one, the bottom of the hydroxides will exhibit the more basic nature. And already we said that beryllium hydroxide has amphoteric nature. That means that beryllium hydroxide can react with both acids and bases. That's why we confirm that beryllium hydroxide has amphoteric nature. And coming to the halides of this group elements, in case of beryllium it forms beryllium chloride. So here that beryllium chloride can be exist in the chain form as mentioned like that. Whereas in vapor phase, it exists as a dimer. So in solid state, it exists as a chain structure, whereas in vapor phase, it exists as dimer. So that the dimeric form can be represented as there are two bridged chlorines are present between the two berylliums and the terminal one chlorine. So here the two bridged chlorines are indicated like. So in a vapor phase, that beryllium chloride exists as a dimer, whereas in solid state it exists as a linear polymer. Okay. Coming to the next point, that salts of oxoacids. So mainly these metals will form salts with oxoacids and forms carbonates and sulfates. So actually these carbonates and sulfates, that thermal stability gradually increases down the group. With increase in the size of the cation, the stability also increases. So especially these group elements forms the carbonates of the formula MCO3. Here that M carries +2 oxidation state and carbonate carries -2 oxidation state. Actually these carbonates are unstable. So on thermal heating they liberate carbon dioxide. Along with formation of oxides. Coming to the sulfates, these group elements also form sulfates of the formula MsO4. MsO4. This is the general formula of sulfates. So actually all these are white solids. They are stable to heat. Actually they are readily soluble in water. That solubility of these sulfates gradually decreases from top to bottom. So the greater the hydration enthalpy of beryllium and magnesium, they can overcome the lattice enthalpy of factor. That's why their sulfates are soluble in water. So here the top of the element beryllium and magnesium will be more hydrated. That's why their salts are also highly soluble in water. Whereas down the group, rest of the other elements from calcium to barium, the size of the central atom increases. That's why hydration decreases, so that solubility gradually decreases from top to bottom. And coming to the next salt, nitrates. Actually these nitrates will be produced by the dissolution of carbonates with nitric acid. So that nitrates having the formula MnO3 twice. So it is nitrate is the monovalent, that group element is the divalent. That's why you can write the formula MnO3 twice. So actually these are also unstable. On heating they decomposes to give oxides and nitrates. So here let us take that element may be either beryllium, magnesium, calcium, strontium or barium. They on decomposition produce oxides along with the liberation of nitrogen dioxide gas and oxygen gas. So these are the common simple things that are observed in the second A group. And today we discuss the last content, that is anomalous behavior of beryllium. So already we said that the top of the element in any group can exhibit somewhat different properties than the rest of the other elements in that group. That's why that behavior is nothing but anomalous behavior. Here the top of the element in this group is beryllium. So due to the small size of beryllium and highly electronegativity and high polarizing power and absence of d orbital, it is somewhat exhibit different properties than the rest of the other elements. In that, first one is that beryllium has exceptionally small atomic and ionic sizes that does not compare with the other members of the group. So that's why that beryllium ionization enthalpy is very high and its small size, which are largely covalently compounds and get easily hydrolyzed. And second thing is that maximum coordination number of beryllium is limited to 4, whereas the other elements can be more than 4. The main thing is the absence of d orbitals in the beryllium. Its coordination number is limited to only 4, whereas in case of other elements of in this group, they can expand the d orbitals. That's why they exhibit more than 4. And coming to the oxides and hydroxides of beryllium. So these oxides and hydroxides of beryllium possess amphoteric nature. That means they can react with both acids and bases. And finally, that beryllium is diagonally related with aluminum. So even though aluminum does not belong to in this group, that size of the aluminum plus 3 ion is similar to that of beryllium plus 2. That's why even though they do not belong to the same group, their chemical reactivities will be the similar and they form similar type of compounds. So those can be explained by the 4 points. One thing is the aluminum and beryllium is not readily attacked by the acids because of the formation of protective oxide layer. So especially aluminum forms aluminum oxide, beryllium forms beryllium oxide as a protective layer. And second thing is formation of hydroxides. Whenever the hydroxides dissolved in excess of alkali, they form the complexes tetrahydroxy beryllium 2 and tetrahydroxy aluminum 3 ions, which are called aluminate ions. So similar type of compounds can be exhibited by the beryllium. And third one is the chlorides of the both beryllium and aluminum. They can be bridged through dimerization, as like mentioned in previous one. So in both BeCl2 and AlCl3, they will be dimerized in vapor phase. Here chlorine bridges are attached to the central atom. So both chlorides and will be soluble in organic solvents like Lewis acids because they can accept electron pair. They are used as a Friedel-Crafts catalyst. Let us take an example of AlCl3. So AlCl3 can be used as a Lewis acid in organic reactions, especially in Friedel-Crafts reaction. And both beryllium and aluminum has a strong tendency to form complexes, with beryllium a coordination number of 4 and aluminum has a coordination number 6. Okay, so these are the anomalous behavior and diagonal relationship of that beryllium of second A group. Okay, so this is all about the general properties of second A group element. Okay, thank you.